Today I'm going to talk to you guys about weight. Now, weight is different than mass, and so we have to make sure that we understand the differences between the two. So mass is a kind of a weird concept. Remember that mass is how much matter an object has inside of it. And if you think about it from last unit, mass was actually the measure of the inertia in the object. So it's kind of the resistance to a change in motion. So the way I like to think about it is the more stuff something has inside of it, in other words, the more matter it has, the more difficult it is to change its motion because you're trying to change the motion of each individual particle that's inside of that object. And so the more particles, the harder it is to change the motion of that object. That's why it's more difficult to stop a oncoming train, a real train, than it is to stop an oncoming toy train, because the amount of particles that you're trying to stop is much, much, much greater for a real train. But it turns out that the other aspect of mass is that it has this gravitational interaction. So here I've drawn the Earth, and what I want you to think about is this. Everybody thinks about gravity, but they don't really spend a lot of time thinking about it, or think about it in a qualitative, or in a quantitative way. Everybody thinks about it in kind of a qualitative way, like, oh yeah, things fall down. And people think they have an understanding of it, but in reality, some of the understanding that they have is pretty flawed. So let's take a look at it here. First, I drew a little guy in green here, and he is standing on the surface of the Earth. Obviously, it's not to scale. That's okay. So the question I would have for you is, what force does that guy feel that keeps him stuck to the planet? And if you said gravity, of course you're right. So gravity is this force that pulls the guy down towards the center of the planet, towards its center of mass. And all objects that are on the Earth feel this pull towards the center of the Earth. And that's called the force of gravity right there. So that force of gravity right there, we can abbreviate using this terminology right here, F sub g. So F sub g tells us it's the force of gravity. So this guy is feeling a force of gravity. Now, we're going to find out later on that it turns out that any two objects, any two masses, will feel attracted to each other because of their mass, because the masses produce a gravitational field. So typically you don't feel it unless there's a lot of mass there, and that's why you only are really attracted to the center of the Earth. You're not attracted to the table or the floor or your car or anything, because they don't have enough mass to really feel it. So any two masses are going to have that kind of attraction. So because of that, it turns out that the guy who's standing on the surface of the Earth actually applies a little bit of a pull back on the surface, or on the center of mass of the Earth itself. But I think you'd agree, his mass is really tiny, and so the force that he applies must be really small, because he is not going to attract the planet like the moon would or the sun would, something like that. It turns out that, again, the force of gravity always applies acts towards the center of the Earth. And so if we have a little cat over here, that cat on the surface of the Earth also has a force of gravity. It's a little bit smaller than the man's, and it is also towards the center of the Earth. And it turns out that the Earth itself gets pulled backwards as well, gets pulled towards the cat. But again, like I said, this pull on this huge mass is very, very small, and you'd never be able to measure the change in motion that results as a result of that. Some people think if you're in the International Space Station, so I drew that up there, if you're in the International Space Station, there's no gravity. But the question I would have then is, what causes the International Space Station to stay in orbit? The answer is gravity. So you can't have it both ways. You can't have no gravity, which is why they float around inside, and then there is gravity, and that's what keeps it in orbit around the Earth. So there must be something weird going on there. We're going to talk about that in just a minute. It turns out there is a force of gravity that's acting, again, towards the center of the Earth there. I tried to draw it there. You get the idea. Anyway, so force of gravity is a force that occurs between any two masses. The bigger the mass, the greater the force. It turns out, too, that the closer the two masses are together, the greater the force of gravity as well. So we could be thousands and thousands and thousands of miles up above the surface of the Earth, and we might not have the same force of gravity that we would on the surface of the Earth as a result, because we're farther away from it. So there's all sorts of things that we can talk about with that. But for now, it's important to remember that the force of gravity is a force between any two masses. The larger the mass, the bigger the force, And the closer they are, the bigger the force. And we'll talk, like I said, we'll go more into depth on this later on. So this force of gravity acts on any object on the surface of the Earth. Actually, it acts on any object on the surface of any planet or moon. And so as a result, we can draw it as a vector right here. So we're going to draw it as a vector. A vector is just an arrow, so it points in the direction of the action, and also the length of it shows us how strong it is. So this guy right here is feeling a pull in that direction, and we say that is the force of gravity acting on the guy right there. Why is it in that direction right there? Because it's the it's acting towards the center of the Earth, and if we assume this is a horizontal surface, then the center of the Earth would be straight down. It's always going to be straight down, so if it's a horizontal surface. So that's the force of gravity that's acting on the object. Now, you may notice that the topic for this conversation is not force of gravity, but weight. And so why haven't we talked about weight yet? Well, it turns out that this is the weight. So oftentimes, or sometimes you'll see old school textbooks will say, instead of S of G, they'll say W, which means the same thing. It's the weight. Now, in the United States, we measure our weight in pounds, and it is totally okay in engineering to measure forces in pound force. However, in the metric system, in our MKS subset of units, we have to use some other units to measure it, and those units that we use for all forces, no matter what they are newtons. And so we're going to measure in newtons in here, after Sir Isaac himself. And those newtons are actually equal to the units kilograms times meters per second per second. So you can see, just as a refresher, you can see why we don't do this all the time, because we deal with forces a lot. You don't want to have to keep writing this over and over again. It's much easier to write newtons each time. Anyway, so the force of gravity is measured in newtons. It's the same thing as the weight. So why doesn't this guy fall through the Earth right here, right down to the center of the Earth? And I think you'd agree that there must be something that's stopping him, and that something that's stopping him is the surface right here. And that floor or the ground, whatever he happens to be standing on, is the thing that's supporting him. And so there must be some sort of supporting force. And because of what we know about Newton's first law, if the forces balance out, then the object doesn't change its motion. And if he's just standing there, he's not changing his motion. So therefore, we know that the forces must balance out. And so whatever this size force is downward, there must be an equal sized force going upward from the floor. That sized force from the floor has a special name, and it's called the normal force. And it's called the normal force because it is perpendicular to the surface on which you're standing. Now, perpendicular, is a right angle right there. That perpendicular word right there is what we mean when we say normal. We don't mean not strange, we mean perpendicular. And so there's a normal force. You could also say the supporting force too. What's crucial to understand though is that this force and that force cancel each other out. Now this force has a cool property, and that cool property is it's actually what you feel when you feel like you weigh something. So if you've ever gone on the Giant Drop or some other rides like that where they drop you, Goliath, for example, in that first hill when you go almost straight down, there's no normal force, and you feel like you are weightless. Your stomach kind of floats up a little bit, you feel kind of strange. And that's because there's no normal force. There's no force supporting you any longer, and that feels weird to us because we're not used to it. If you ever go into a high-speed elevator and you feel either a lot lighter going down, like your stomach's kind of rising up a little bit, or feel a lot heavier going up, again, that's because of the normal force. So let's go back to our International Space Station issue. So if we got the International Space Station, inside the International Space Station there's an astronaut, and that astronaut floats around inside. And the reason why the astronaut floats around inside is because he is not subjected to a normal force. He still has weight, he still has a gravitational force, otherwise he wouldn't continue to orbit the Earth, he would just fly straight off, according to Newton's first law. But because he has weight, he continues to move in a circular path. But he doesn't feel like he has weight because he doesn't have a normal force. So the normal force is where we get our feeling or a sensation of weight. And so weight is a complex topic. But it is one that I think you'll find you have a lot of fun with, especially when you go to Six Flags, because roller coasters and most of the rides there, they play around with your normal force. And that's how they make you feel weird as you go through it. There's either less normal force or more normal force. There's less when you're going down a hill or falling. There's more normal force when you're going through a loop or you're turning really fast, things like that.